Welcome. In this session, you will learn how to scale write throughput and transactional throughput for your applications. Let me start by illustrating the kind of businesses that will benefit from this session. Let's say you are in the business of e-ticketing. So you sell tickets for popular events such as soccer matches or popular concerts. And the way it works is that as soon as you put your tickets on sale, fans rush to purchase the tickets as fast as they can. So here you get a very high throughput of transaction per second as soon as you put the tickets on sale. Another example of business that would benefit from this kind of session is simply retailers, e-commerce retailers, because obviously if you run an e-commerce platform, you get a lot of transactions per second. A final example could be an e-trading application where your users trade assets with one another or with your platform. And in this case, again, you get a lot of transactions per second. So overall, with those three businesses, what I want to illustrate is that any business that needs a high throughput of ACID transactions per second, or a lot of write operations or strongly consistent read operations, they would benefit from this session. So you may ask, what do I mean by strongly consistent read operations? Well, let me explain. In distributed database systems, you typically have the main database, and you may have read replicas that are here for high availability or data resiliency. And those read replicas, their state is replicated asynchronously with the main database. Those read replicas can be used for read-only operations. However, due to the asynchronous nature of the replication, you cannot be sure when you perform a read operation in those replicas, you cannot be sure that this read operation reflects the latest state of the database. It will eventually do so if you allow enough time for the replication to take place, but you cannot be sure that it is the latest state. So if you want to perform a transaction, or you really want to know what items are actually still available on sale, then you need to perform a strongly consistent read operation, meaning a read operation that for sure reflects the latest state of the database. So overall, to translate in technical terms what the kind of businesses that I have listed need. This kind of businesses need a lot of write operations per second, a lot of strongly consistent read operations per second, and overall they need a lot of transactions per second. And as well, those businesses have database sizes, table sizes that keep on growing. So if this is your case, well, you are in the right place, my friend. This session is for you. So where you are currently right now, you probably already have an application running and you are using a relational database for this application. And you know what? It's actually a good choice. You did right starting with a relational database. Why? Because a relational database offers a lot of flexibility in the data access pattern. You can store all the entities of your data model in the same schema, meaning that you don't get data silos. All your data is stored within the same schema. All your entities are stored in the same schema in a normalized form, which is great, again, to avoid silos or duplication. Moreover, relational databases offer a lot of flexibility in the data access pattern, and this is great for startups because, you know, as a startup, you pretty much put your business upside down and inside out as you get customer feedback. And you need to evolve your service, you need to evolve your solution. And for that, data access pattern flexibility is very important. So I would definitely recommend to the kind of businesses that I have listed earlier, I would definitely recommend them to start with a relational database. But as their scale grows, they will have no choice to switch to a database solution that can scale out. And in that case, they need to use a sharded database system. And this is what we are going to talk about in the rest of the session. However, because switching to a sharded database system requires a lot of refactoring from the application side, and it's also, a change of paradigm. So because it's quite a big change to switch from relational to sharded database system, you may consider implementing a workaround first that will allow you to kick the can down the road before actually switching to a sharded system. So what kind of workaround am I talking about? Well, the idea of such workaround is, instead of directly committing your transactions to the relational database, your application can simply place in a queue, buffer in a queue, transaction requests. And then an application, a piece of code, will pull that queue in order to attempt to commit those transaction requests in the relational database. So here the idea is that the queue will absorb the transactional requests, and the database can catch up on the backlog of transaction requests within the queue. It can catch up on this backlog in its own time. However, this kind of solution only works, obviously, if user demand still offers frequent enough moments of respite for the relational database to catch up on its backlog of transaction requests. Moreover, with such solution, keep in mind that you can't directly send a confirmation to your users that the transaction was a success, because you don't know if it's going to be a success until the transaction is committed. When the transaction request is sent in the queue, you have no idea whether, when attempting to commit it, it will fail or succeed. So in order to send an acknowledgement to your users, you're going to have to use a change data capture that will listen to the transaction logs in order to identify successful transactions and therefore send an acknowledgement to your users. So what you see with this workaround is that it's not so great in terms of customer experience, because imagine you want to purchase a ticket for a music concert. You have been waiting for so long for this band to come to your place. You attempted to purchase it, you provided your credit card information, and then you get a message saying, "Thank you, we will come back to you." And then 2 minutes later, or maybe even more, you receive an email saying, "Sorry, we were not able to perform the purchase." How would you feel as a customer? Well, pretty bad. So this kind of workaround, it allows to keep the relational database for longer, but it's not so good for the customer experience. And moreover, this workaround only works if the user demand still offers frequent enough moment of respite for the relational database to catch up on its backlog. So at some point, you're going to have no choice but to switch to a sharded database system. So let's talk about them. What is a sharded database system? Imagine that you have a huge table, and this huge table is powered by a single database node. Obviously, the write-throughput and the transactional throughput for this huge table is going to be limited by the amount of resources available on the node powering it. And my mama always said, if something is too big to swallow, just slice it up. And that's exactly the idea of sharding. Basically, you're gonna slice up, you're gonna slice up this huge table into different chunks. And those chunks are called logical shards. And to each of those logical shards is going to be assigned a database node. So just to clarify, actually I said to each logical shard you have a database node. Actually, to be more specific, this database node is for transactions, for write operations, for strongly consistent read operations. However, under the hood, the logical shard is also replicated on two other database nodes for data resiliency purposes. But because this replication is asynchronous, you can only use those replicas for eventually consistent read operations. Because this is not the subject of this presentation, in this presentation we only care about transaction, we care about write throughput and strongly consistent read operation throughput. We will forget about those read replicas, about those eventually consistent replicas. So please keep in mind that they exist for data resiliency purposes, but we will not represent them in the rest of this presentation because this is not the subject. So again, you have one database node per logical shard. And what happens if one logical shard becomes hot, meaning that it receives too many transactions per second, too many write operations per second, too many strongly consistent read operations per second? Well, it's becoming hot, just slice it up again. Now that we have seen the big idea behind sharding, I would like to go deeper with an example. First of all, usually when we talk about sharding, we are in the realm of NoSQL databases. I know Oracle databases does offer the option to implement sharding. But usually, when we talk about sharded systems, we talk about NoSQL databases. But even NoSQL databases often offer SQL-like interfaces. And this is, for instance, the case of Amazon DynamoDB, which allows the option to use PartiQL in order to issue operations. Using PartiQL is absolutely optional, but I'm going to use PartiQL operations because I think it's easier to read for my audience than if I were using API calls to the DynamoDB API. So anyway, in this example, I am defining a table, and I just have to specify what column is going to be used as the sharding key. So here, what will determine whether a row will be assigned to one logical shard or another? Well, that will be the value of its email column. Here you see I'm talking about table, column, rows, but really we are in the realm of schemaless databases. So we are in the realm of documents databases or key value databases. So here, what I call a row is simply a JSON document. Each JSON document, each item, as they are called in DynamoDB, each row, each item is uniquely identified by its primary key. And then you have whatever value you want as a JSON payload. You see here that the primary key and the shard key is exactly the same thing. But this is because I have defined the primary key as only one column. It is also possible to define the primary key as the composition of two columns, the sharding key as well as a sort key. So what identifies uniquely each item, each row, is the combination of two columns, the email and here the entity type. For information, when you have two items that share the same value for the sharding key, but obviously have a different value for the sort key, well, those items that share the same value for the sharding key, they are called items belonging to the same item collection. Okay, let's go back to my example. So here I have defined a table with a composite primary key, and I want to insert a new document with the sharding key value leo@gmail.com. What is going to happen is that the request will first hit a routing layer, and that routing layer will decide to which database node, to which logical shard this new item should be sent to. So how is this routing layer going to work? Well, it's going to use, obviously, the sharding key. It's going to look at the value of leo@gmail.com in order to determine where to send that item. And the way it works usually is that it computes a hash of that sharding key. Some systems, instead of relying on a hash, they rely on intervals of possible values for the shard key, but here we're going to focus on those that use a hash. So the way it works is that the routing layer computes the hash of leo@gmail.com, and it will see in which interval of possible values for the hash this specific hash of leo@gmail.com falls. It just happens that it falls within that interval, and so the routing layer knows that this item has to be sent to database node 2, to logical shard 2. Please note that actually the way I'm presenting it is an oversimplification. Actually, the routing layer doesn't exactly rely on an interval of possible values of the hash in order to map to a specific database node. Instead, it relies on a hash ring thanks to the algorithm called consistent hashing algorithm. So when I'm presenting things as an interval, it's actually an interval of possible values for the hash. It's an oversimplification, but it still works. So just stick with this idea. You don't need to understand hash rings. Anyway, thanks to this algorithm, the routing layer is able to know that this item should be sent to database node 2, and database node 2 is going to add this new item to its logical shard. And you may ask, okay, so how does database node 2 add this new item? Does it simply add this new item at the end of its data file? Well, for the case of DynamoDB at least, actually each database node organizes its items, its rows, according to a B tree. So it's very similar to B-tree indexes as you see in relational databases, but here the leaf of each leaf of the tree is not composed of a row ID, of a pointer to the data. Instead, it contains the actual JSON data. So each database node organizes its data according to a B-tree indexed by the shard key as well as the sort key when one has been defined for the table. Because I'm talking quite a lot about DynamoDB, let's introduce some DynamoDB lingo. Actually, in DynamoDB, what I call a logical shard is called a partition. I hate that. I hate that they call it a partition. I think it's very confusing. Logical shard is the standard naming, but I don't make the rules. So yeah, partition equals logical shard. Moreover, DynamoDB is a serverless service. So as a user, you have no idea and you don't need to know how many database nodes are being provisioned to power your table. Nor do you know, as a consequence, how many partitions are being created for your table. Also note that, I was telling you that the routing layer, it can be either client-side or server-side. In the case of DynamoDB, this routing layer happens at the server side, so you don't have to worry about it. But just for your information, some systems, such as for instance Memcached, they handle the routing layer at the client side. And developers don't have to implement this. They simply use the client library, and the client library makes sure of implementing that routing layer. So let's continue with another example. This time you want to update an existing item. And you see here, in order to update it, you have to specify the partition key, meaning you have to specify both the shard key as well as the sort key. So the request is sent to the request layer, to the request routing layer, and the latter will compute the hash of leo@gmail.com, and thanks to the value of this hash, it will determine that if any node happens to have the relevant data, it has to be node number 2. It will send the request to node number 2, which will look in its B-tree index, and because that B-tree is indexed by the shard key as well as the sort key, accessing the relevant item is going to be very efficient. And obviously, database node 2 will then update the affected item. Another example, this time you want to read all the items that have the shard key leo@gmail.com. Again, the routing layer will compute the hash value for leo@gmail.com and determine that if any node happens to have relevant items, it has to be node number 2. Node number 2 will receive the request and look into its B-tree, which again is indexed by the sharding key as well as the sort key, but here we're not specifying the sort key, and it's going to return all the relevant items that have this specific sharding key, leo@gmail.com. Pretty efficient. Let's spice things up a bit. What if you would like to run a query where you don't specify the shard key? Here, name is not the shard key. How can the request router know where are the relevant rows, if there is any? I mean, the table has been sharded according to the email column, not the name column. So here you have two possibilities. Either the request router is going to send the request to each and every one of the nodes that are involved in powering your table. And then each of those database nodes will have to look into its data. The thing is that each database node has organized its data according to a B-tree indexed by the shard key and the sort key. Here, name is not the shard key. So basically, the B-tree structure will be of no help, meaning that each database node will have to look at each and every one of the leaves in order to identify potentially relevant rows. That means that each database node will perform a full table scan. And because each database node is involved, it's called a global full table scan. As you guess, this is extremely inefficient and should be avoided. Another possibility is that maybe beforehand, before running that query, you have created an index. But here, what we call an index, it's not a B-tree index. Here, when we talk about an index, it's actually another table. But this time, this other table is sharded according to the name column instead of the email column. So data, whenever you write data in the main table, which is sharded according to the email column, whenever you write data in the main table, the write operation is also asynchronously propagated to that other table, to that index that is sharded according to the name column. This means that every time you perform a write operation, the write operation is twice as costly. And that's the same thing for the storage. It takes twice as much storage because here, unlike with relational databases B-tree indexes, you can't reference a row ID. You can't reference a pointer to the data because you have no idea that you can't be sure that the data will reside on the same node. I mean, those two tables are those two tables are sharded according to a different key. So you just have to duplicate the data. That's why indexes are quite costly. You can't create them in all directions. Moreover, in the case of indexes that use a different shard key, the replication is asynchronous. And because of the asynchronous nature of the replication, you cannot use this kind of index for strongly consistent read operations. This means you cannot use this kind of index for transactions. So anyway, for ACID transactions, this kind of index will not do the job. As you can see, sharded database systems come with constraints. And thanks to this example, I can illustrate the three tenets that a transactional sharded database system should respect, and what are the drawbacks, the trade-offs that come with each of those tenets. The first one is that a transactional sharded database system is built for scale. It's built for very large table. And as a consequence, global full table scans will take a lot of time. They will perform very poorly. And therefore, they have to be avoided. The second tenet is that you want to have stable and predictable performances for read operations. We are not talking about analytics. Here we are talking about a transactional system. So you want your read operations to execute within a reasonable amount of time. And for that reason, you have to avoid global full table scans. And for the same reason, you also have to avoid filter predicates, I mean where, on anything else than the shard key, because otherwise, as you have seen in the example just before, it would require a global full table scan. And again, for the very same reason, you should avoid joins and aggregations on anything else than the shard key, because once again, it would require a global full table scan. And actually, for that very specific reason, in Amazon DynamoDB, joins and aggregations are simply deactivated. You can't perform them because Amazon wants to force you to respect that tenet of stable and predictable performances for read operations. So you want to have stable and predictable performances for read operations, but you also want that for write operations. And for the very same reason, you should avoid write operations that don't target the sharding key. And actually, in DynamoDB, it's simply impossible. You have to specify the sharding key as well as the sort key if one has been defined for the table. So the consequence of those tenets and of their accompanying trade-off is that you have to think very hard from the get-go of what is your data access pattern. And you're going to have to model the entities in your table in order to respect those tenets. And basically what it means is that you're going to have to denormalize the entities of your microservices within the table in order to avoid joins. And you're going to have to think very hard of your data model, and you're going to have to stick with it. It's basically you're going to get married with your existing data access pattern. Earlier, I have said that DynamoDB willingly restricts some feature in order to force you to respect the 3 tenets that I have just mentioned. So for instance, DynamoDB doesn't allow you to perform joins or aggregations. And you may ask, why? Why doesn't DynamoDB still offers me the flexibility to do bad things? Well, because the philosophy of DynamoDB is constant and predictable read and write performances, whatever the scale. So DynamoDB wants to force the stakeholders, wants to force developers and data modelers to integrate the constraints and the tenets that come with a sharded transactional database system, so as to force them to respect those tenets. DynamoDB is not meant for search, it's not meant for reporting. If you need that, you're going to have to duplicate the DynamoDB data into an Elasticsearch or into a lakehouse. But the idea is that you should use the right tool for the right job. DynamoDB is the right tool for high write throughput at scale and high transactional throughput at scale. It's not meant for reporting or search. Other sharded database systems, such as Oracle Database and MongoDB, when they are sharded, because they are not necessarily sharded, but even when they are sharded, they still offer you the flexibility to perform things such as aggregations and joins. But be mindful of what SQL features or what MongoDB features you're using, because such operations will incur global full table scans and basically will lead in terrible performances. Use the right tool for the right job. So I said that DynamoDB ensures stable and predictable performances, whatever the scale. What about this predictable? Can I give you a number? Yes, I can. With DynamoDB, each partition can achieve a throughput of up to 1,000 write operations per second and 3,000 strongly consistent read operations per second. So this means that for your whole table, which is composed of many partitions, you will get a very, very high throughput. Please keep in mind that the figures that I give you are about read and write operations when they are performed in isolation. However, when they are performed as belonging to an encompassing ACID transaction, then the performances are divided by 2. So each partition will deliver a throughput of up to 500 writes and 1,500 read operations per second when they belong to an ACID transaction. And obviously, an ACID transaction can span several partitions, and actually, they can even span several tables. And you may ask, okay, but what happens if one partition becomes hot? What happens if one partition gets close to that limit of 1,000 writes per second or 3,000 read operations per second? Well, DynamoDB will simply split the existing partition into 2 so as to go away from that limit. So previously here in this partition, you had one item collection, meaning a set of documents that share the same value for the sharding key, as well as another item that has a distinct value for the sharding key. Because this item collection and that item have a distinct value for the sharding key, DynamoDB can, if it chooses so, split the partition and assign therefore a distinct node for each of those partitions. And therefore you go further away from this limit, the partition can cool down. And then what happens if that partition here gets hot? Because all the items in this item collection all share the same value for the sharding key. The value is for all of them leo@gmail.com. Then the items of this item collection cannot be separated. They cannot be separated. Therefore, partition splitting cannot be performed here because all those items share the same value for the sharding key. And yes, in this situation, you will end up throttled. This partition will get throttled as it will potentially reach the limit of 3,000 read operations per second and 1,500 write operations per second. So that's why you have to be mindful of your choice of partitioning of sharding key, because you want to avoid a situation where you will end up with one or several partitions getting throttled. So today you have seen the benefits of sharded database systems for your transactions. You have seen that such systems allow to virtually scale out infinitely the write throughput, the strongly consistent read throughput, and overall the ACID transaction throughput. However, sharded database systems come with constraints. Those constraints are that you're going to have to think from the get-go of what is your current data access pattern, and you're going to have to model the entities in your table in order to get efficient access with this current data access pattern. But because you are modeling accordingly, basically you will have to denormalize your data, and because you're modeling according to your current data access pattern, you're pretty much getting married with it, because changing your data access pattern will mean having to remodel the entities within your table and pretty much put upside down your existing code. So that's the drawback of using a sharded database system. But at scale, yes, it's worth going there. Thank you very much.